All right, day 2. Perfect squares, perfect cubes, and their roots. Now, I just want you to think back to elementary school. I want you to think back to those big bins of the base 10 blocks that the teacher would bring out. You guys can recall back to that? Those big blocks? So what did you have? You had the little units, right? What shape were they? The little units. They were squares, right? That represents 1. Is 1 a square? What's 1 times 1? 1. So is 1 a square? Yeah, 1 is a square. What was after the square? They had those rods, right? That was 10. Those were worth 10. Those base 10 blocks? Is 10 a square? What was the shape of that thing? It was a big rectangle, right? So 10 is not a square. Take the square root of 10. Do you get a perfect number? What was the next shape after the rod, the long rectangle? The flat? The flat? What was the flat worth? 100. Is 100 a square? What was the shape of it? Can you take the square root of 100 and get a perfect number? 10, right? What was after the flat? The cube? That was 1,000, right? So is 1,000 a square? Is 1,000 a square? Is 1,000 a cube? What's the cube root of 1,000? 10, because 10 times 10 times 10, right? What's the cube root of 100? Is 100 a cube? No, so if you took the cube root of 100, it wouldn't be perfect. You wouldn't get this nice number. So when I want you to think about perfect squares and perfect cubes, I want you to think that they could make those shapes. This is not magic. They just come from reality. Perfect square, it has to be a square. How do we represent a perfect square? Well, it's a shape of a square. And what symbols do we use for that? X to the power 2. Can you think of a perfect square? Maybe the one I just used. 100. If 100 was the square, what would be the square's root? Or in other words, what's the square's length? 10. Do you remember the rod in the base 10 blocks was a length? It was a rectangle, right? A length. So it's the length. So what would be the root of x square? Yeah, just x. So the root is the length of the square. Similarly with the cube, how would you represent a cube? You'd have to draw a square, and then you'd have to draw another square that's the same size. That wasn't very good. And then you'd connect those edges. And now instead of talking about area, we'd be talking about volume. And in the base 10 blocks, which one was the cube? Which value? 1,000. So there's 1,000 in here. And what was the cube's root? The cube's root is another word for length. What's the length of that cube? 10. 10 this way, and 10 that way. Length times width times height. What's 10 times 10 times 10? 1,000. So hopefully you guys start to make these connections. That the square is the area, and the root is the length, and the cube is the volume, and the root of that cube is the length. Hopefully that is okay. Any questions before we move on? All right. Mic check. All right, here we go. Let's do this. Oh, all that got recorded. Great. All right, let's keep going. Parts of a radical. Do you guys recognize the square or the radical there up top left? I almost said square root. That would have been a mistake. What kind of root is that one? Cube root, because they have the little index written as 3, right? Take a look at part C there, though. That one doesn't have the index. If the index is not written, what do you assume it to be? The square root. Okay? So if it's not written, it's the square root. Okay? If the little 2 is not there, oh, it's not there, it's a square root. Otherwise, they'd have to tell you what type of root it is. Okay, the whole thing is called the radical. That's in green there. The whole thing is the radical. The thing inside is called the radicand. Not the radicant. The radicand. Right? You guys are cans, not cannots, right? The radicand is the number on the inside. The whole thing is called the radical. So let's take a look at the first one. What radical is that guy? A. How would you say that? The what? Nope. Cube root of 27. Okay, cube root of 27. So someone said 3. What does that mean? The answer is 3? Okay, sure. If you put that in a calculator, you would get 3. It means that if you had a cube that had a volume of 27, the edge length of that cube would be 3, right? Since 3 times 3 times 3 is 27. Can you find that one in the calculator? Depends which calculator you have. If you got mine, you must hit the math button. And it's the 4th one down. Okay? Okay, how about the next one? Whoops. How about the next one? What's that one? If the last one was the cube root of 27, this one is the... What kind of root? Not a cube root, it's not a 3, it's a 5. So you'd say 5th root. So what's the 5th root of 32? Now you're thinking to yourself, okay, well what's a 5-dimensional shape look like? So the geometry analogy is lost after dimension 3. Once you get to like the 4th root, like what is that, right? Hypercube. 5 dimensions, like Tesseract. You guys ever see the movie Interstellar? He's in that bookshelf. You guys ever see that movie? Me and my son watched that movie like 3 times in the IMAX, and we always have that joke, like, where's the 5th dimension in the bookshelf? So, anyways, the answer to this is 2. Why? Beautiful. Love it. 2 times 2 times 2 times 2 is 32. Okay, how do you find the 5th root in the calculator? Well, after the 3rd root, they don't really care about it anymore. So what they have, if you hit the math button, they have this x root. But you have to type the 5 first. So hit the 5, and then hit the math button, and then hit the x root. And then that'll allow you to do the 5th root of 32. Okay? Do you guys need me to show you that on the screen? All right. Yeah. So if you want to do a 4th, a 5th, a 6th, a 7th, and so on root, I'll do a fifth root. You have to hit the 5 first, then the math button, and then this x root. And then type in 32, and you'll get what you need. Okay, how about the next one? What is the next one saying to us? 3 multiplied by the square root of 5. So for this one, I would literally just go into my calculator and go 3 times square root 5. Okay? Is 5 a perfect square? No. What kind of decimal are you getting? Something random and crazy? Is there a pattern in those digits? Do you guys know what type of numbers those are? Where there's no pattern in the decimal, it doesn't stop, there's no pattern. It doesn't repeat, and it doesn't stop, and it doesn't repeat. What's it called? Irrational. Good. So, any non-perfect root, and I'll jot this down for you. Any non-perfect root is irrational. How do you know if something's irrational? Just look at the decimal. Is it random and crazy like pi? It's irrational. The next one is on the page just because some people really struggle with their calculator because they don't understand order of operations. What you have here is like some invisible brackets. And it's not really like, some people just don't realize it. So we're going to make this very clear. There's brackets here. It's 3 take away root 5, the result of that, divided by the result of 5 plus root 3. So if you put this in the calculator, do 3 minus root 5 in a bracket, and then hit the divide button, and then another bracket, 5 plus the square root of 3. If you're rocking like an old school calculator that does not have brackets, do 3 take away root 5, hit enter, do 5 plus root 3, hit enter, and then take those two results, divide them. Three minus root 5, 5 plus root 3. Take those numbers and divide. I got about 0.11. You guys getting that? 0.1134. Okay. That's going to show up on the test, by the way. What I get, 1, 1 or something? And then like dot, dot, dot. So make sure you know how to do this basic stuff on the calculator. If you can use a calculator, you're going to get a bunch of free marks in this next test. Okay? Yeah. What calculator are you using? Got to put in brackets, right? Oh, you got them. You got these mixed up, 5 and 3. And now this fancy chart. Okay, let's do this together. X is the root. Write this down. X is the root. X squared is obviously the square. And x cubed is obviously the cube. Now we'll do these one column at a time. Follow along with me, please. 0 times 0 is? 1 times 1 is? 2 times 2 is? 3 times 3 is? 4 times 4 is? And so on. And this list could go on forever, but we'll stop at 12, just like most times tables stop at 12. Just an arbitrary choice. Let's jump to the cubes. These ones are much harder to remember. 0 times 0 times 0. 1 times 1 times 1. 2 times 2 times 2. 3 times 3 times 3. 4 times 4 times 4. 5 times 5 times 5. How do you know this? 6 times 6 times 6. How do you know this? You have these memorized? 7 times 7 times 7. You did this already while I'm talking? Is this 512? 729? 1000? Then I have no clue. 133331 or something? 1728? That's like a rap song, right? 1728. It's the cube of 12. No? Come on, you guys. You were feeling it. All right, that chart, I'm going to get you guys to memorize this procedure for this calculator. Watch this. Everybody, hit the y equals button. Make sure it's all cleared out of there. There's nothing in there. You might remember, like, from grade 9, like, some relationship and function stuff where, like, you had, like, y equals mx plus b. You guys remember that? So for this one, the function is the square. We want to take the x and square it. So that's like the input-output machine, those function machines. So take your input x, which is right here beside alpha. Right here beside alpha, hit x, and then hit the power 2 button. It's right next to alpha. Hit the x button, and then hit the power 2 button. If you learn this, then in the next couple lessons, this is going to become so valuable as a resource. So please follow along with me. Go down to y2 and hit x power 3. See how I got the x squared function and I got the x cubed function? Now I'm going to go second graph. Take you to the table. The table is yellow here, so you need second graph. And it generates those for you instantaneously. Okay, let's keep going. We got that list generated. Now we have some work with prime factorization. Okay, 1296, using prime factorization. You with me on this? And then we're going to determine the square root. This is going to be crazy. The power of prime factorization. 1296. Does it divide by 2? What do you get? $12.96 divided by 2 is $6.48. Does that divide by 2? Yes. $6.48 divided by 2 is? Keep going, divides by 2 again. $162 divided by 2, you get 81. This one divides by no. No. Oh, nothing. Okay, let's keep going. So I got the prime factorization there. I just repeated one so that you could see that it kept going on the chart. So what's the prime factorization of 1296? How many 2's do you have? 4. And how many 3's do you have? Is there 4 of them? There's 3 of them. Is there 4 of them? I think there's 4 of them. Yeah, I divided 81 by 3 and I got 9. That's incorrect. 81 divided by 3 is, there's 4 of them, 27. Divide out 3, you get 9. Divide out 3 again, you get 3. Now I got like way too many of them. Okay.
Could you please come to the main office? Thank you.
Okay, sorry about that prime factorization. Putting it in the second column for some reason messed me up. That's the proper prime factorization. You guys okay with that? All right. Now, I want you to think about an easy one. Let's think about like 4. Is 4 a perfect square? What are the prime factors for 4? 2. And there's 2 of them, right? What about 9? What's the prime factors for 9? 3 and 3. So for perfect squares, those primes come in pairs. Why do primes come in pairs for perfect squares? Good. You got to make a length and a width out of the same value, right? So perfect squares come in pairs. So for 1296, how many pairs do you have for the 2's? 2 pairs, right? And for the 3's, you also have 2 pairs. Okay, so what you want to do is take a single prime out of each. So for this one, you take 1, because you just want the length, not the length and the width. For this one, you take 1. For this one, you take 1. And for this one, you take 1. Times all those up, you get 36. Check the square root of 1296. 36. Okay? I'm going to pause the video. You guys are going to try the next one on your own. Okay, so keep working. I'm just going to quietly do the prime factorization on my own. You can double check with my work. So that's nice. I got 2 2's, 2 3's, 2 7's. How many do you need from each pair? 1 from each pair. So 2 times 3 times 7 will be equal to the square root of 1764. 2 times 3 times 7 is 42. And if you double check the calculator, if you just do it straight like that, you get it. So primes. Primes are like the elements in chemistry, the elements that make up the compounds. The primes make up all the composite values. And you can only ever have a perfect square root is if the primes come in perfect pairs like this. If you ever have one prime that's like left off, hanging off to the side without a pair, they're not a perfect square. So let's try a non-example. Let's see if you guys got some room for a non-example. A non-example would be square root 10. What's this prime factorization for 10? 2 times 5. Are they in pairs? And so it's not perfect. What about square root 20? What's the prime factorization for 20? 2 times 2 times 5. The 2's are in a pair, but the 5 is not. So that one's not perfect. What if I add another factor of 5? Times that by 5. Then I'm at 100. 100 would be 2 times 2 times 5 times 5. Do those ones come in pairs? So then that one is good. This one makes me happy. These ones make me sad. Okay, so for perfect squares, the primes have to come in pairs. Now you're smart people. What about perfect cubes? What do they have to come in? Perfect triples. Good. If squares come in pairs of primes, perfect cubes come in triples of primes. Whoops. Where are we now? Oh, my buddy, 1728. Okay, divide by 2. No, 1728. That's the rap song, right? 1728? No. I'm urban, guys. I know. Okay, obviously I'm just joking. 216 divided by, oh my gosh, lots of 2's, hey? Oh brother, this is just taking forever. Finally, they stopped coming in 2's. Now we can get to the 3. 9, 3, 3, 3, finally down to 1. So if you want, I'll switch colors now to red, get your attention. If you want cube roots, they got to come in triples. Are they in triples? So then, how many do I need out of each triple? Just one. 2 from this one. 2 from this one. And then 3 from this one. 2 times 2 times 3 is 12. And that was the cube root of the 1728 from the last page. Okay, you guys try the next one. 2744. You guys try that one. Get the prime factorization and then put the primes in triplets. Okay, so there's the prime factorization for 2744. You got a triplet with 2. You got a triplet with 7. And the important thing is that there's no other extra prime hanging around. That's it. They're all grouped up perfectly. So then grab 1, 2 from that triplet and grab 1, 7 from that triplet. You get 14. So there's the cube root of 2744 with primes. Then it would not be perfect. Yeah, wouldn't be a perfect cube root. And it wouldn't make the shape of a cube. It'd make the shape of like a rectangular prism. Okay, a little bit of problem solving with algebra. So I'm just going to do these. So a cube has volume 4,913. If you'd look at your data sheet, you'd find the formula for the volume of a cube like this. And then it's going to ask me what's the surface area. If I use my data sheet and I found surface area, I'd have this. Let's think about those for a second. The first one, volume equals x cubed. That's just length times width times height when they're all the same. X times x is the same as x cubed. Length, width, height, they're all the same. Think of the Rubik's Cube. X times x times x. What about the surface area? How many faces on a square? That's why we have the number 6. And then what's the area of one square? X times x is x squared. So I've been given the volume. So where does that go? Where does this go? Gets substituted right there. 4,913 equals x cubed. How would you solve for x? It's kind of like the Pythagorean theorem, but we can't do a square root. We got to do a cube root. Like, what's the opposite operation as cube? Cube root. So you cube root both sides. and you get x equals whatever that is. Is it exactly 17? Like, pick nice ones, hey? 17. Now, I have the value for x, so it goes right there. Surface area is 6 times 17 squared. Remember your order of operations. What do you do first? Do the 17 squared first. That's exponents, and then you multiply. So 17 times 17 times 6. 1734. This would be, we're in inches, so inches squared. Doesn't look like we're going to have a lot of time for homework, so if you want to stick around and do homework, you're going to have to come, or just hang out in the east block. Show that 729 is both perfect square and perfect cube. What do you think we have to do? Could you just square root and cube root both of them with the calculator? You could. But that's not a beautiful thing. It's not really showing anything. It's just, can I plug into a calculator? So everybody take the perfect square, take the cube of 29, 729. What do you get? Okay, so if you take the square root of 729, you get 27. And if you take the cube root of 729, you get 9. So 729 appears to be a really interesting number. This has not really demonstrated to me that you know much other than how to punch into a calculator. So what other alternative do we have? Beautiful, prime factorization. Long and not useless, just long. So 729, do it. Prime factorize it. Now is for you. Okay, you finish off the prime factorization. You continually divide by 3 over and over and over again. You get 3 to the 6th. That's the answer to 729. If I was to write all those 3's out, you can put them in pairs, or you can put them in triples. And if you put them in pairs, nothing is left over, and if you put them in triples, nothing is left over. So it's both a perfect square and a perfect cube. Let's keep going. Let's do this last one. Actually, this last one is for you. I'm not going to help. It's very similar to the first one. So you guys try this last one on your own. So you guys can take a look at the assignment in the east block. You're welcome to stay if you like. And tomorrow I'll make sure the lesson is shorter so that you guys have time to work on this assignment and the new one that comes tomorrow.